see your screen.
Really?
Just so you know, because I don't want you to be like recording and then you're looking at like Tinder or something and getting embarrassed. Anyway, so now that we're recording, even though no one's here yet except you, that's okay. I'm sorry, and last name?
Reed.
Reed, that's right. Chloe?
Huh?
Chloe?
Keandra.
That's right, Keandra. I'm so sorry. We have a Reed and a Reedy. And I've been gone and we've got face masks and it's hard. Anyway, let's talk about some basic stuff that probably everybody knows anyway, so it's okay that they're missing this. Let me ask you this. I need you to let me move here so you can see it better and so the camera can see it better. Yeah, that'll work. What do you think is going to happen? This is a bottle of dye. What do you think is going to happen to this dye when I put a drop of it in that water? Do you think that drop's just going to stay there in that one little spot, or what do you think?
I think it'll diffuse, like it'll go.
There we go. It'll spread out, right? And like you said, the word is diffusion. So there we go. One drop. Okay. Maybe I had too much water. There we go. So I know you probably can't see it on the screen, but the clear water is starting to turn a little bit pink, right? Because I put a red dye in there. I'll hold it up. Maybe you can see. I don't know. Anyway, yes. And that's diffusion. Diffusion is a really basic concept, right? It's when something goes from an area of high concentration to low concentration. So that dot was high concentration, right? Because that was pure dye. And when I put it in the water, there's no dye in there, so it's spread out. One of the things that's not mentioned in this lab that you do need to know is that when diffusion happens like that, it goes until what's called equilibrium is reached. So it went until, it might even still be going a little bit. It'll spread out until it's a nice equal color. You know what I mean? Same thing, imagine if I were to light a scented candle right here. At first, you wouldn't smell it, right? At first, it would just be, I could smell it. And then it would diffuse out because, that's that area of high concentration. And then you could smell it. And then he could smell it. And for a while, it would be really heavy in this part of the room. But eventually, the whole room would have an equal scent. Does that make sense? Like it wouldn't be stronger from one part to the other because it would go until it reaches equilibrium. So that's diffusion. Very simple concept.
I have a question.
Yes.
So for the lab, I usually do click like submit. We just click share, right?
Yeah. As a matter of fact, technically, you might not even need to hit share. It should be automatic.
Okay.
But yeah, definitely hit the submit button.
Okay.
So yeah, that's diffusion. Do you have any questions about diffusion? No questions? All right. How about this? I tried to draw. It's a bad drawing. Imagine if we had like a U-shaped tube, right? And I've got a little thing right here, and we'll talk about what that little thing is, but it's a membrane. Some things can move forward and backwards, some things can't. Here on the right, obviously, it's a really high concentration of particles, whatever kind of particle it is. And here on the left, it isn't, right? So where would the particle, do you think these particles are going to move right, or do you think these particles are going to move left? If we're talking about diffusion, if everything else is normal, what do you think would happen here?
I think the rest of them will just move with the other ones.
Yes. These are going to move to the right because diffusion says things want to go from an area of high concentration to an area of low concentration, right? That's just what diffusion is. And it would happen that way. However, this is where things get a little bit different and we're no longer talking about diffusion. This little membrane, it allows water to go back and forth, but it won't let these particles go through.
How is it going to get over there?
So it won't, right? So in that situation, your cells or whatever it may be, it still wants to reach equilibrium. So what's going to happen now, instead of the particles, I'm going to abbreviate, so the particles going that way because they can't, what happens instead is the water goes the other way. The water will flow in here until, of course, there's not much room. I should have drawn it a little bit different. Until the water level got really low up here, down here, and that water level would rise. And then eventually, because the water level was so low on the left side, and it got higher technically on the right side, eventually we would have equilibrium. Because see how that now looks even?
Yeah.
And that's what osmosis is. Osmosis is when water diffuses. But in this case, it was diffusing to balance things out. So that's how that works. So are there any questions about just the general concepts of diffusion and osmosis? All right, pretty simple. I'll leave that on the board. The next thing, hopefully this is big enough for you to see what's going on. Now we're actually going to talk about these experiments. So in the first experiment, you guys are going to put dye in something called auger. Do you mind holding that up for them so they can see it? Or she has it. It's okay. I didn't know it was right here. I'm sorry. So you've got this auger in there, which is basically like a clear gelatin, like a gooey substance, basically. So what happens is, you've got that.
Oh, I see it. I didn't see that first.
Yeah, it looks clear, but there's actually stuff in there. So what'll happen is, you're gonna put dye on there. You have two different dyes. And I'm gonna go through this quick because I'm not worried about like the instructions. You will have those written down for you. I'm just making sure you understand the concept. So you have this stuff called potassium permanganate and methylene blue. Do you happen to remember which one's the big one? The larger molecule size? That's the larger one?
Yes.
Okay. So what happens is you're going to put this little bitty speck. You're going to have methylene blue on one side and do a little bitty speck, and the other one on the other side, potassium permanganate. The name doesn't matter. The fact is you have just two different dyes. You could just call it dye A and dye B for all I care. The name for potassium permanganate, that's not important. The point is you have two different dyes. You can put a little bitty drop on that little dish. Now, one of these things, even though they look the same to you, the molecules are different. So one of them is bigger than the other one. And I'm sorry, you said the methylene blue.
Yeah.
That's the larger one?
Yes.
Okay. So methylene blue, this is the larger of the two. I'm going to put a big L next to it. Large. That's the large, even though, again, it looks the same to our naked eyes, but it's a larger molecule. The potassium permanganate, it's smaller.
Yes.
So what you know from doing the pre-lab, and you guys are way over there, so I'm going to take this off. And I'm pretty much as immune as you can be now since I've had my shots.
Both of us.
Yeah. So we're good. So again, you're going to have these little dots, and they're going to look normal to you. That you won't be able to tell a difference at first. Hopefully they're nice and uniform. And what's going to happen is it's going to diffuse out, right? You know that because you've done the pre-lab. And you should know from the pre-lab that things that have a smaller molecular size should move farther. Therefore, since the methylene blue is the larger one and the permanganate is the smaller one, I would expect the potassium permanganate to move less. But what's going to happen, again, you'll start and you have a little bitty dot and you're going to measure it. And right here, well, I'll come back to that. And every 15 minutes, you're going to look at it. And it's going to get bigger and bigger as time goes on, right? You might look at it in 15 minutes, it looks like that. And you might look at it in 30 minutes, and it looks like that. And you might look at it in an hour, or you will look at it in an hour, and it might look like that. Does that make sense?
Yeah.
You just put a little dot on there, some dye, and it's going to spread out.
So, for the dye, will we put it in like two different ones?
Yep.
Okay.
One on each side. You're going to have a dot of the methylene blue of the larger one, and then a dot of the smaller one. That's what you do. Now that's the simplified version of what's going to happen. That's just the one, right? So you're going to have the one that you do that. But to make things a little bit more difficult, you're actually going to have three different petri dishes where you're going to do that. One of them is going to be cold, one of them is going to be at room temperature, and one of them is going to be warm. You can do the same thing that I drew here, except again, one of them is going to be in the refrigerator, one of them is just going to be out in the room, and the other one you're going to put on a warm plate. Does that make sense? So again, what we're looking at here, we're looking at two different things. We're going to see how size makes a difference. We're going to see if the larger methylene blue goes faster or slower than the smaller potassium permanganate. That's the one thing we're looking at. And the other thing we're going to look at is this speed effect. So will a warm temperature make things go faster, or will they make things go slower? And that's what the first experiment is going to be. And I've got the data up here, or the tables that you see on your lab. That's this right here. So when you do it, put your data on the board so we can take a picture of it so all your classmates can share your data. And I'm going to give you an example because I don't know what it's going to be. Let's say you start off and you're looking at the methylene blue and you're looking at the one in the refrigerator. It starts off at 0.5 centimeter. And then 15 minutes later, it's 1 centimeter. And then 30 minutes later, it's 1.2 centimeters. 45 minutes later, it's, 1.8 centimeters. And then 60 minutes later, maybe it's 2 centimeters. I don't know, I'm just making those numbers up. And that's what you're gonna look at. And you'll have your data for the cold, you'll have your data for the warm, and the room temperature. Now here's where it gets a little bit tricky. You definitely wanna, how am I gonna put this? This is a little bit hard to do, because you're gonna put a little speck of dye on there, and it's not always a perfect little dye. So this one might start off right away when you put it on there, it might be 0.5 centimeter long. And you might mess up the other one, and it might be 1 centimeter to begin with. And the other one might be, I don't know, 0.8 to begin with. Not because of anything to do with potassium permanganate or the color or the heat. That's all because maybe you just didn't put it on there the right way, because it really is tricky. So that's important to think about, because, let's say you go through all this and that ends up at, I don't know, 1.8, and it's got data in between there. And then this one goes and it ends up at, I don't know, 0.9. Now you might look at, let me do something different. That one we would have. Yeah. Let me do something different. So really, what I'm getting at here is it's not just the end number that matters, because you have to look at where it started. Because you want to see which one moved the most. So if you started off with a really big circle and it only got a little bit bigger, then that's different than if you started off with a really small circle and it got bigger. So that's why, and this is important, pay attention to this, because this is not on the data, this is not on the worksheet. Under this, somewhere on scrap paper, you don't need to show me the work if you don't need to, but you need to do the math and tell me how much did it move. So this one went from 0.5 to 2, so that means it increased by, what, 1.5. Right, and then this one went from 1 to 3, so that's 2. So just do the math, because really what's more important is not these numbers, it's this number. I don't know why it's not on that lab, because what's more important is how much did it grow? Because that's what you're looking at. If it grew a lot, did it grow a lot or did it grow a little bit? Because we are expecting the smaller one to grow the most and the one in the warmth to grow the most. That make sense? Okay, and he's here to help. I'm gonna have to leave after this, but he'll be here to help. So there's that. All right, so that's the first experiment. The second experiment is pretty simple too. You're gonna have a beaker. It's gonna be smaller than this, and it'll be just water in there, and I've drawn it right here. And inside that, you're gonna have like a little cell. You're gonna make like a version of a human cell, basically. It's just a little piece of plastic, but basically it's supposed to act like the cell membrane would. So anyway, in that cell, you're gonna have starch and sugar. Excuse me, starch and salt. Yes. And then you're gonna
starch and salt?
Yep. And you're gonna put that little cell into that beaker of water. Now, what's going to happen is, well, let's talk about what happened. We know this is going to be pure sugar, good grief, pure salt. I'm just going to abbreviate S, and pure starch, ST, whatever. So what do we know about diffusion? What's that starch going to want to do? Since if we're going to talk about diffusion, what should that starch want to do? Stay in there or leave? And to remind you guys, because you guys are late, this is a good time to remind you, don't be late. You're going to lose points for being late and leaving early. But what you guys missed was we talked about diffusion. Diffusion is when something goes from an area of high concentration to low concentration. I put a drop of dye in here, and it didn't stay there. It spread out, right? And if I light a candle, that scent isn't going to stay here. It's going to spread out because it wants to go from an area of high concentration to low concentration. So if you have this cell that has just starch in it, and it's just sitting in a bunch of water, what's that starch going to want to do? Stay in the cell or go out? Go out, yes, because it wants to diffuse, right? That's a highly concentrated starch, and there's no starch surrounding it. It's going to want to diffuse. Same thing with the salt. You have salt in there, you don't have salt in the water, so it's going to want to diffuse. Of course, the difference here is starch, as you know from chapter 3, is a really big, long molecule. So even though it wants to diffuse out, we don't know if it can. It might be too big to make it in and out of the membrane. Salt is really small, so maybe it can diffuse out because it's small. However, salt is also polar, because it's an ion. We don't have time to get into that. So there's things that we don't know. Maybe it can, maybe it can't. And that's what this experiment is going to find out. Will the starch leave? Will the salt leave? And then the other thing is, will the water go in? That would be osmosis. And to find that out, here's how this is going to happen. And here's how you're going to fill this table out. And if you look at it online, it's already started for you. Let's talk about the substance in the cell. I just drew it. I told you what's in the cell. The thing that's in the cell to begin with is nothing but salt and starch. So here you'll have, whoops. Can you tell me what this says?
Yeah, water,
Water,
iodine,
iodine,
salt,
salt,
and starch.
and starch. All right. So I told you already, if we're talking about what's inside the cell, at the beginning, the only thing that's there is salt and starch, right? There's no water inside the cell, it's on the beaker. There's no iodine, that's also going to be in the beaker. So that's how you're going to start, and it's already given for you, so don't mess with that, right? It's already the way you need it. Also, the substance outside of the cell, again, you're going to have it in this beaker. So the question is basically, it says what's outside of the cell, but another way of wording that is what's in the beaker. And the only thing in the beaker is, to begin with, water, and you're going to put a little drop of iodine, or some drops of iodine on there too. So this is the way it looks at the beginning. It's already like that for you. Does this make sense? You see what this shows you, right? It shows you that this is inside the cell and nothing else is, and this is outside of the cell to begin with. Does that make sense? Okay. Then you're going to check it again in 30 minutes. Now, if it got larger, if this thing got larger, what does that tell you? Did something come out of it, or did something go into it if it got larger? Into it, right? It would have to. If something got bigger, something must have gone into it. And we would know it's most likely water, right? Most likely the water is going to go in. That's osmosis. However, like I said, you're putting a drop of iodine in the water. And hopefully you remember from last week, when you mix iodine and starch, it gets really black and like dark, right? You can see it. So at the end of the 30 minutes, if this cell is turned dark, that obviously means the iodine went in there and reacted with the starch. Does that make sense? If at the end of the 30 minutes that starch is dark, because it's not dark to begin with, if it's dark at the end, that means the iodine went in there and made it dark. If it's not dark at the end, that means you know the iodine is still only on the outside of the cell and it's not on the inside. Likewise, after 30 minutes, if this water is a little bit dark, that must mean the starch came out of the cell, right? Because it's interacted with the iodine in the water. So those are the ways you're going to be able to tell which things are where. Did water come in? Did starch come out? Did silver come out? One last thing to tell you about that. With the silver, I said silver, I'm going to say starch. This is starch, right? Silver and the salt, I think is what goes together. Okay, so you're also, not only are you going to put drops of iodine in there, but you're going to put drops of like a silver thing.
Yes.
And what happens is when the silver mixes with the salt, it makes like a milky color, not color, but like a milky substance.
Yes.
So if after 30 minutes, your water isn't clear and it looks all cloudy and milky, that must mean that the salt came out because it is then reacting with the silver. That makes sense? And I know I'm saying this quick, but you don't have to memorize this. You just have to do it. And as you're doing it, he'll be here to remind you what your data means. Like, oh, the fact that this is dark means this. The fact that this is cloudy means that. So he can help you with all that. So again, that's how table 2 is going to go. Let me erase table 1 because you're going to need to put in your actual data, not the hypothetical stuff I put in there. Speaking of hypothetical, very quickly, I'm going to put in some hypothetical data for this. If at the end of this there's water in the cell, like if it got larger, you would put an X there. If there's not, you don't put an X there. If at the end of the experiment there's iodine inside the cell, like I said, if it's cloudy inside the cell, then you would put an X there. Right? If there's not, then don't put an X.
So if we don't put an X, will we just see, like, type in what it looks like after the 30 minutes?
Yeah, and not even type it in. You just put an X if it was there and leave it blank if it wasn't.
Okay.
So again, like if you put the iodine in the water, but then after 30 minutes in the cell, the starch has turned dark, then you know, you can put an X. Like, oh yeah, there's definitely iodine in the cell now because it turned dark. And again, he'll be there to help you interpret it. But as the way it starts, This column and this column you don't need to touch because it's exactly the way it needs to be. There is no water or iodine inside the cell to begin with. There is no salt and starch inside the beaker to begin with. So that's it. Any questions about number 2? All right, number 3 is even easier. If you understand number 2, you're really going to understand number 3. It's the same concept. You have a beaker of water. You can make a little cell. This time, instead of having salt and starch, you're going to have sucrose. And all you're going to do is weigh it. You're going to weigh it at the beginning, and I'm just going to put in some hypothetical things. Let's say maybe it's 5 grams to begin with, and then you weigh it again in 15 minutes, and it's, 6 grams, and then in 30 minutes it's 7, and 45 minutes it's 7.5, and then in an hour it's 8. You could look at this data and say clearly that thing got bigger, right? And the only way that could get bigger is if water went into it, because there's nothing else to deal with. There's water on the outside and sucrose on the inside. That's it. So if it got bigger, water must have gotten in. Likewise, if you start off and maybe it's 5 to begin with, and then it's 4.5, and then it's 4.3, and then it's 3, and then it's 2. Clearly, it got smaller, right? So then if it got smaller, surely the sucrose went out instead of the water coming in. It's that easy. That's all I really have to say about that one. And then the 4th one, the eggs, you don't even have to worry about that. You did need to do the hypotheses because I wanted you to think about it, but we're not actually going to do that experiment.
So like if we finish like table 3, we just turn it in. Just turn it in.
Yep. So what's going to happen is you should be broken up into teams. Yeah, you should be broken up into teams. Of course, there's only a few of you.
I'll turn it around. I forgot nobody else was here.
I'll let you decide how to do that. If you should break them up into teams, and if so, how you want to break it up. Because it's such a small class, might all be able to just work together on all the experiments. It's hard to say.
Yeah, one can do the dye, methylene blue and potassium permanganate.
Yeah.
And 2 people can do this activity because.
That's true, yeah. So one person, might as well be you since you're sitting there.
Yeah.
You can do this, and then maybe you 2 can do activity 2, and then you can do activity 3. Because number 1 and 3 are pretty easy.
Yes.
2 was the one that's slightly harder.
Yeah.
Requires more work. Now, before I leave, because that's it for this, I'll remind you, it's better to turn your stuff, go ahead and get it in as early as possible. That way I can start correcting you, because it's not due until Friday. So if today you write something incorrect, I can go in there and say, oh, that's not right. You've got until Friday to fix it before you actually get the grade. And I'll remind you, and I haven't been here, so I'm sorry, but make sure you guys are on time. You will lose points for coming in late or leaving early. Bad points. I understand. Just a reminder, because I haven't been here to remind you. So I wanted to make sure I put it out there. So that's it. Any questions about the pre-lab or the lab itself?
Oh no, I have a question for lab 5. That's the pre-lab, right? The one you just said that's due Monday, or?
Yeah, basically Sunday at midnight.
Okay.
Yeah. And just like anything else, you don't have to do it alone. You can meet me online during office hours or schedule times, and I can walk you through each question if you need to.
Okay.
And also, the earlier you get it done, same thing I was saying about this. It's good because if you make a mistake, I can correct you, and you'll have until Sunday night to fix it. And that's it. All right, I'll leave that up there. You guys have a good day. I'm sorry I can't stay.
You too.
Thank you. Don't forget, when you're done with this,